So in this lecture we'll study 3D truss element. Previously we studied 2D truss element. 2D truss element was nothing but a spring element, but at each node there were 2 degrees of freedom, and accordingly we inflated the stiffness matrix of the spring element to make it a element stiffness matrix of size 4 into 4, and this is a 3D truss element. So here at each degree of freedom, at each node there are 3 degrees of freedom, that is displacements along 3 coordinate axes at each node. So there are total 3 plus 3, 6 degrees of freedom. So that means we have to again, so here in this figure you see, this is the spring element, and this is having a stiffness of K, and this is the local axis of the spring, this XL, and if there is any displacement along this local axis, the spring will offer a resistive force in the opposite direction, and that is also along this local axis. But since we are using it to analyze this, we have to incorporate another, along with the axial degree of freedom, another 2 degrees of freedom. Here also along with the axial degree of freedom, another 2 degrees of freedom, and we have to make this stiffness matrix a 6 by 6 one. So let us take this as the local axis. This has a local axis, so this XL is the local axis, and YL and ZL, this constitute a plane perpendicular to the local x-axis, that is XL axis, and this YL and ZL are arbitrarily taken. So at this node there are 3 degrees of freedom, this UL1, UL2 along this YL, and UL3 along this ZL. And similarly at this node there is a degree of freedom UL4 along the axial direction, and UL5 along this YL direction, and UL6 along this ZL direction. So there are 6 degrees of freedom, but only if you displace it in UL1 direction or UL4 direction, then only force FL1 in this direction or FL2 in this direction will be generated. So you can inflate the stiffness matrix, and it will have non-zero elements at 1 1, 1 4, 4 1 and 4 4. What are the 1 and 4 degrees of freedom? They are the axial degrees of freedom, and we have already seen this process in case of 2D truss element. So now but these type of truss elements are generally used for analysis of tower structures. Also that you have seen transmission towers which carry electric wires. So in these transmission towers we mostly use this 3D truss element. So again, due to the same reason that we have which we discussed for 2D truss element, we have to have a global coordinate system which is common for all elements, because a local coordinate system is different for different elements, but the global coordinate system is same for all elements, and the local stiffness matrix has to be transformed in this global stiffness matrix. Now what is the transformation matrix? So once we know the transformation matrix, then we can use the standard formula. Which we derived in 2D truss element case like this, and we can get the global stiffness matrix. Local stiffness matrix already we know, which we have obtained by inflating the spring stiffness matrix. Now what is the transformation matrix. So what is the relation between, see, uval1, uval2 and uval3, these three components constitute the u vector at node 1. So this is the vector transformation relation. Uval1, uval2, uval3, that is they are three components of the displacement vector in the local coordinate system, and the same displacement vector has three components, ug1, ug2, ug3 in the global coordinate system. Now what is the transformation matrix? As you know, the transformation matrix is this, where this angle is between the local x cos of this element is the cos of the angle between the local x-axis and the global x-axis. This is cos of local x-axis with the global y-axis. This is cos of local x-axis with global z-axis. This is cos of local y-axis with global x-axis. Local y, global y, local y, global z, local z, global x, local z, global y, local z, global z. So this is the transformation matrix. So also you can call it, these are the L, M and N of XL. This XL has got this L, M and N. So this is L for XL, this is M for XL, and this is N for XL. Similarly, this is L for Y local, this is M for Y local, and this is N for Y local. And these are L for Z local, M for Z local, and N for Z local. So this matrix we call lambda. And when we club these two vectors, that is displacement at node 1, this is displacement at node 1 and displacement at node 2, we have to use this transformation matrix. This lambda 0, 0 lambda, and this T is this matrix. Similarly, force vector also transforms according to the same relation. Now, see here, we can always, once we know these two coordinates, we can always find out this LXL, MXL and NXL. But YL and ZL has to be in the perpendicular plane has to be in a plane which is perpendicular to XL. But these two directions are actually arbitrarily taken. Wherever you take, your stiffness matrix remains this once they are perpendicular to XL. So you actually cannot, you can find out, but these can be anything, because you can take YL, ZL here, or you can rotate it about XL to some other position. Then also you can get some LYL, MYL, NN. So these are not unique. This depends on these values. They depend on where you take YL, ZL, which are perpendicular to XL, but where. Okay. So this you can find out, but this you cannot find out in a unique way. So now you find, if you just attempt to get your global stiffness matrix, which is this, then you just multiply the matrix and you get something like this, and here symmetric. So here you write symmetric. See, in this multiplication, after this multiplication and in this global stiffness matrix, you are only getting LXL, MXL and NXL. But LYL, MYL and NYL, or LZL, MZL and NZL you are not getting. So these values are not of importance. These values are not of importance. Only these values are of importance. So you can take anything for these values, because these are in no way going to affect your global stiffness matrix. So this is one interesting point. And once you get the global stiffness matrix, The remaining procedure is same. You assemble the stiffness matrices, put the boundary conditions, and apply the loads, and you solve for the unknowns. So the next element which we will learn is the 2D beam element. So this also we will try to find out the stiffness matrix of this element from first principles. But see, the elements are slowly becoming more and more complicated, and until this beam element we can get the stiffness matrix from first principles. But once this is more complicated, once we consider more complicated elements than this beam element, we have to take help of some other method. Okay, so this beam element, this is called a 2D beam element. So here I have forgotten to show, this is the x-axis or x local axis, you may say. This is the x local axis from here to here. This is the x local axis. Sorry, from here to here, this is the x local axis, and this element has got 4 degrees of freedom. So since this is a beam element, since this is a beam element, this beam element can have a transverse displacement and it can have a slope. So here it can have a displacement and a slope. So we are calling the slope a small rotation. So it can have a displacement and a rotation. Rotation is actually the slope. Here also it can have a small displacement and a small rotation or slope. So we are calling this this displacement we are calling UL1, and this rotation we are calling UL2, and this force we are calling FL1, and this moment we are calling FL2. So UL1 is displacement at node 1, UL2 is rotation at node 1, UL3 is displacement at node 2, UL4 is rotation at node 2. FL1 is transverse force at node 1, FL2 is moment at node 1, FL3 is transverse force at node 2, and FL4 is transverse moment at node 2. Here there is a sign convention. If you take this as your local x and this as your local y, then the rotation is this, so it is positive in the z direction, and we'll take the displacement positive in the positive y direction. So how can we calculate K11? So remember Kij, how did we compute how can we compute Kij, that is force at DOF I due to unit displacement at DOF j, keeping all other DOFs other than j fixed. So here suppose we want to find out K11, then what we will do, we will give only unit displacement here, so delta 1 will be 1, and all other DOFs, that means all these 4 DOFs, that means this rotation here, displacement here and rotation here, they have to be displacement here and rotation here, they have to be taken as 0. So what we did, we have given a displacement here, the slope we have kept 0. So the slope is 0 here at this node. At this node both the displacement is 0 and the slope is 0. And here we have shown F1 and M1. Here we have shown F2 and M2. Now if you find out the bending moment at a distance x from the left end, then as you know, M equal to EI d2y d2w dx2. See, along the x-axis dy dx is positive, and if dy dx is increasing, then d2 dy dx2 is positive, and this bending moment creates a positive d2w dx2. Okay, dy dx is the slope. So dy dx is positive, and if the slope increases with x, then d2w dx2 is also positive. And if you give an anti-clockwise moment, that is responsible for a positive d2w dx2. So here it is positive, and it is f1x. So here if you take moment about this point, so this is m, this is f1x minus m1. So about this point, we are taking moment about this point, m, capital M, minus f1x plus m1 equal to 0. So m is equal to f1x minus m1. Now starting from this, if you integrate, so this is ei dw dx, and the boundary condition is dw dx is equal to 0 at x equal to 0, because here you are not allowed to give any slope. Okay, because other than 1, keeping force at DOF1 due to unit displacement at DOF1, keeping all other DOFs other than 1 fixed. Okay, that means theta 1 has to be 0. So once you use this, then your C1 will become 0. Now you again integrate. So EIW is this, again W equal to delta 1 at x equal to 0. So that is one boundary condition, W equal to delta 1 at x equal to 0. So that gives you C2 equal to this, or delta 1 equal to this. Now at the right end also, at x equal to L, dw dx equal to 0. So here you put here in this, here you put, so C1 is 0 anyway. So at the right end, ei dw dx equal to f1 L square by 2 minus m1 L. So that is 0. So here you get a relation between m1 and f1. So eiw is this. Now at x equal to L, w equal to 0, that is the fourth boundary condition, which gives you this. And from here, if you take f1 by delta 1, that means force at 1 per displacement at 1, that means force per unit displacement at 1 equal to 12 vi by L cube, that is K11. So in this way you can find out K11. Similarly, if you want to find out K12, for K12 this delta 1 should be equal to 0, only displacement will be given at 2. So theta 1 will be given only, and here delta 2 is 0, theta 2 is 0. So for K12 it is F1 by theta 1. That means force at node 1 is F1 due to unit displacement at node 2, that is force at 1 due to unit displacement at 2, that is theta 1. So this is F1 by theta 1. So in the same way you can find out, in the same way like this, you can find out F1 by theta 1 and get the value of K12. Now what would be K34? What is the diagram for K34? So force at 3 due to unit displacement at 4. Unit displacement at 4 means this is positive theta 2 given. So this is the fourth degree of freedom, theta 2 given, and delta 2 0, delta 1, theta 1 0. And you have to find out K34, that means force at 3, that means F2, force at third degree of freedom, that means F2 due to unit displacement at fourth degree of freedom, that means theta 2. So this is F2 by theta 2. And also you can find out these K values from Castigliano's theorem. Here we have shown you one example how to find out K11 from Castigliano's theorem. So we have already seen that the bending moment here is this bending moment. This bending moment here is what is the bending moment here is this. So if the bending moment is this, so what is the principle of Castiglione's theorem. The principle of Castiglione's theorem is you remove the supports here and show the support reactions, but at the same time you have to keep it statically determinate. So at the right end the full support is kept, and at the left end the supports are removed and the corresponding reactions are shown. So this is the bending moment, and this is the strain energy. So this is the strain energy. Now del u del F1 is equal to displacement in the direction of F1, that is delta 1. So delta 1 is this, and del u del M1 is theta 1, which has to be 0 for K11. So this is 0. So this is this. Now you use these two equations and find out F1 by delta 1, and you get this as your stiffness. So now if you now find out all the stiffnesses, so the stiffness matrix is now a 4 by 4 matrix, then you get this Ke. So this is the stiffness matrix for this. This is the stiffness matrix for this two-dimensional beam element. So FL1, FL2, FL3, FL4 is it, because for our convenience we'll call it F1, 2, 3, 4, but actually it is force at node 1, moment at node 1, force at node 2, moment at node 2. And here it is UL1, UL2, UL3, UL4, displacement at node 1, rotation at node 1, displacement at node 2, rotation at node 2. Okay, so with this we stop here, and we'll see in our next class how to find out the stiffness matrix of this 2D beam element in an alternative way, or in a more general way, which we can apply for other complicated elements.